Okay, in this lesson we're going to discuss how to calculate stress states in a 2D stress state. So let's remember from last time that we have a stress tensor that's composed of 6 values. There are 3 normal stresses and 3 shear stresses, and then these 3 stresses here are repetitive. Okay, and we talked about last time how we have a given stress state, and what we want is to realign our coordinate systems to put everything along a principal axis. And very often we might have something that looks like this. Notice that there are zeros. 3 of our values for the stress tensor are equal to 0. The normal stress and 2 of the shear stresses are equal to 0. So this happens in reality quite often, that we can make this 2D stress assumption. And so what we're trying to do is we're trying to take the applied stresses, and by realigning the coordinate system we're going to express them as principal stresses. And there are 2 types of principal stresses. There are normal and shear principal stresses. So let's have a look. Here's what our applied stresses look like. Notice, just as a reminder, this is infinitesimally small element. This might be a little piece of a bracket somewhere, maybe right in the middle of the bracket or on the edge or somewhere. And there are some stresses that are being applied. Most likely these coordinate systems, this x direction and this y direction, have something to do with the creation of the part and nothing to do with the loading conditions that are being applied to this little piece here. And what I want to do is I want to move coordinate systems by some angle, phi, so that we're expressing a maximum normal stress and no shear stress. And so we would say that this is the principal normal direction. All of the normal stresses are always mutually orthogonal to each other. And we also could, at this point, make another coordinate transformation 45 degrees away from the original, so that the normal stresses are equal to 0, and now we have our maximum shear stresses. Okay, so now we have computational devices that make this transformation very similar, but that hasn't always been the case. In the past, it was a lot more difficult to do the calculations, and so a graphical method was developed. You've probably seen it before. It's the Mohrs circle. So let me get all the information on the slide, and then we'll talk a little bit about what we see. First, we have our stress cube, or our stress tensor, and we recognize in this stress tensor we do not have anything in the z direction, so there are 3 of the components that are missing. And so what we're going to do is we're going to let the abscissa be the normal stress. That's what you think of as the x-axis. That's the normal stress. The ordinate is the shear stress, or what we'd call the y-axis sometimes. And 90 degrees on a Mohrs circle is really only 45 degrees in space. That's kind of the trick of the whole procedure, is this recognition. And in this class we're only going to deal with with materials that have the same properties in every direction. If that was not the case, then we would care about the largest principal normal direction. We would actually care about the direction that causes the normal stress. In other words, we'd care about what that transformation looked like. Okay, so with all those there, what we can do is we can plot sigma x, tau xy for our first coordinate system. Notice clockwise is considered positive, so this is a positive tau xy. And then sigma, so that creates one point right here at C. Then we have another point, sigma y and tau xy, that's D. And then what we're going to do is we're going to construct 3 circles. We recognize one point is where the circle that connects the taus to each other, so that creates a diameter in a circle. We're going to see where that crosses the normal axis in 2 places, and we're going to construct a circle there. That's one circle. And then we're going to construct a circle from those points to the origin. So there's the second circle between P2 and P3, and another circle between P1 and P2, and that's what we're showing here. The beauty of this method is that we can see graphically that the maximum normal stress is on the far right of the normal axis. The minimum normal stress is on the far left. Now that might be zero, or it actually might be a compressive load, as this picture is showing compression. And the maximum shear is at the topmost point of the circle. Why do we care? Well, something happened to do, if we can get some rules having to do with the sigma 1 and sigma 2 and sigma 3 and this tau 1,3, this maximum shear, we can make some sort of failure criteria to know whether this element will fail, whether the material is strong enough. That comes a lot later, but that's why we care about this. So let's do an example by hand first. So here we have, notice there are 3 elements to our stress tensor, and we're going to assume the other 3 are equal to 0. If we're going to do this by hand calculating it, the first thing we would do is construct our stress matrix. It would look like this. So 40 and 20 are the normal, and notice minus 10, because this is in the counterclockwise direction, are the shear elements. We're going to call some matrix A that has the eigenvalues introduced, and those are what will become our principal values. We set the determinant of that matrix equal to 0. The formula for the determinant of a matrix is fairly simple, so we just apply the formula and do some arithmetic and calculate what the shear stresses are. Okay, so this is going to be 30 plus or minus some value. If I did my math correctly, it's going to be 44.1 kpsi, 15.9 kpsi, and I also am going to have 0 as the third stress. So there's always going to be 3 normal stresses. If it's a 2D stress state, we're going to assume the third one is equal to 0, and now what I have to decide is what order to call it. I'm always going to take the highest value, and that'll be sigma 1. I'll always take the middle value, and that'll be sigma 2, and I'll take the lowest value in sigma 3. In the example we just looked at a few minutes ago, the lowest value was a negative, so this number definitely could be a compressive instead of a tensile stress, and if so, then we would have let that be sigma 3. Okay, so that's one way to do it. I also could do this in MATLAB, so let me pull MATLAB up here. It looks like I've already done it. So I made up this matrix called sigma, or sig. It's 40 and 20 and minus 10. It's the same matrix. And then I took eig of sig, and I got the same answers, 15.85 and 44.14. So there's 2 different ways of solving the same problem. What I'd like to do next is show you a third way of solving the problem. It's kind of an introduction into the graphical way of doing things. So what I'm going to do next is I'm going to open Inventor. Find it, there it is. And before we can actually talk about the problem, I need to give you a little bit of an introduction into the Inventor workspace. So when you first open up Inventor, we have the options here of new and open. But before we do that, we need to decide where we're going to put files. This is not something that's common with some of the other programs, so I'm going to go through this. I'll set it up for the first time with you right now. So I'm going to click the Projects button. What I'm doing right now is determining where I'm saving my files, and CAD packages care a lot more about where files are saved than Word documents or other types of files, so we need to be very careful about that. I'm going to create a new project. This is going to be a new single user project, so I'll click Next, and I'll call this ME466 class. And this is where I'll do anything that we do in class. Notice it's in my users documents. It looks like it's going to set up a folder called Inventor, and inside that we'll have something called ME366 class. So next, we're not going to have any kind of libraries. You can see I don't have any located here anyway, so I'll just click Finish. And it's warning me that it's going to have to create some new folders, so we'll go ahead and do that. Check mark shows that it was created successfully and that this is now the project that I'm in. So I'll click Done. And now I'm ready to actually create a new part. In this class, we're going to be dealing with parts and assemblies. I'll go ahead and click New. You can see there's some standards that I've set up for different classes. What we'll want to do for this example is just choose a standard .ipt. This is just a standard part. We'll click Create. Okay, now we are looking at the screen. A couple things I want to point out to you. First off, we have our model space. This is where the 3D image is going to be. You can see there's a coordinate system. Right now we're staring at the front plane. We're looking at the X and Y axis. This is called the view cube, and it provides a quick way of manipulating the space. So now I'm looking at a 3D or isometric view, or let me go back to the front view. So that's a convenient way to rotate the part around. It also does a zoom extents when you press that. So we'll find that we'll use that a little bit. Looking up at the tabs up front, let me just talk a little bit about what each tab has to offer. This first tab allows us to do 3D model operations such as extruding or revolving or sweeping or creating holes and those types of things. We can also do feature movements such as making patterns or mirroring, and we can create work surfaces, planes and axes and points. In the sketch toolbox, and most of the stuff is grayed out because I haven't started a sketch yet, but this is where we'll be able to create lines and circles and all of the sketch type tools that we do to make geometry, as well as dimensioning and setting in design constraints. The Inspect tab just has some distances if we need to make some measurements. Tools also have the same items as the Inspect, but they also have some other ones such as setting the material and the appearance, as well as some of the settings for the documents. We might need to get in there occasionally to modify some things. The Manage tab, the most important one here, and we probably won't use it much this class if at all, is setting up driving parameters. So I could make some things that scale, make the entire part a little bit more intelligent if I needed to make a lot of changes to the part. We probably won't use much of this element in the class. We can turn on things like the center of gravity. We can switch what types of things we're seeing on the screen, and all that's done in the View tab. And that's it for now. There's one other when we're dealing with assemblies that I'll show you in another lesson. So let's go back to the 3D model, and I'm going to go ahead and start a 2D sketch. I have the choice of which plane I want to start it from, and I'm going to pick the XY plane here. We'll open a new sketch, and here we are inside the sketch with the origin located in the center of the screen. Now, the first thing I want to do is I want to recreate the points that were given in the problem. So if you recall, sigma x was equal to 40, sigma y was equal to 20, and tau xy was equal to -10. So let's create those points. Here's a point, I'll just drop it in space. Now I have a readout, and I could try to do a little zooming, but I'm going to let the dimensions take care of themselves. I do know it was a negative value, so clockwise is positive and counterclockwise is negative, so we'll make our first point be up here, and we'll make our second point be maybe somewhere here. Alright. Let's go ahead and put some dimensions. Now these dimensions are going to be off when I start, but hopefully they'll get better as we go along. The first dimension I'll put in as 10. Notice it's off the screen. If I click front, I'll zoom to the extent and I can see it again. Let's put another dimension from the origin out. This will be 40. And again, let me zoom out so I can see everything. Now the next one, I'm going to hit escape so I get out of the dimension tool, and I'm going to grab this line, this point, and just move it around here in space. I think it's going to be close to here. I don't have to be exact because we can dimension it. I'm just kind of moving it around so it's not too hard to grab it. Click my dimension tool again from 0. That's pretty close. Well, it needs to be 20. And now we'll do 10 in the downward direction. Alright, now the reason we did this was so that we could create a circle that has a diameter between these 2 points. So let's do that. Let me go ahead and make a circle. I'm going to put my circle as close as I can to the x-axis and let it contact the point, and you can see that it's telling me it's going to create a constraint, making sure that circle is touching that point. So I'll accept that. If you see that it's green, that means it's not fully defined, and it means that you still have the ability to move things around. Okay. So if I grab the circle and I start dragging out again to that point, so after I've moved it around, what I want to do is I want to add a constraint. And the constraint I want to do is a coincident constraint. I want this circle to be coincident with this point. There we go. It's almost fully constrained. The only other thing I want to make sure is I want to make sure that this point in the center of the circle is on the x-axis. And to do that, I'm going to use a horizontal constraint. So I'll click the center point and the origin, and that's going to force that circle's center to be on the origin. That fully constrained that circle. Alright, so now I want to identify the 3 important stress points. These are my 3 principal stresses. So I'm going to grab the point tool, and if I'm resting on the circle so that it's snapping to it, it's going to snap to quadrants. So there's one, there's one, and I'm going to go ahead and put one also at the origin. Hit escape to get out of the tool. And now we can draw circles. There's a lot of different ways to do it. I'm going to do it one way. I'll probably show you a different way in class, but whichever way works is fine with me. I'm going to take a circle and grab it until it connects to that point. And at this point, I'm going to go ahead and fully constrain this circle before I continue. So the first thing I want to do is I want to make sure that the center is horizontal with the x-axis. And I also want to make sure that this circle is coincident with that origin. And it looks like, if I zoom in, it looks like the point that I dropped did not really snap to the quadrant. I don't know if you can see that very well. Let's see. There we go. So that's a problem. I really wanted this point to be on the axis. So again, I'll use the horizontal constraint. I'm going to grab that point, and I'm going to say that I want it to be constrained to the origin. While I'm doing it, let's go ahead and let this point also be constrained to the origin. By the way, I'm zooming in and out here pretty fast. I'm just scrolling with the middle mouse to zoom. Let me hit the front, so we'll do a zoom all. And I need to make one more circle. I've connected points, let's see, I've got point 1, 2, and 3. I've connected circles between 1 and 2, and between 2 and 3 I just need one more circle that connects 1 and 3. So again, let's make a circle, and I'll again snap it to this point. Use the coincident tool and snap the circle to point 3, and the last one is horizontally. I'll make sure that the center is on the x-axis. So there's my Mohrs circle. Now, for me to calculate what the stresses are, I'm going to take the dimension tool and go from the origin, from 0, 0, out to the furthest point, and I'll click it. It's going to give me an error here, and it's going to warn me that the sketch is already constrained. I don't need to define it, and that's true. All I want to do is look at this to make sure it matches what we think it ought to. So I'm going to choose accept to let it be a driven constraint. It's in parentheses. That means it's not actually defining anything. It's just showing me what's already there. Notice the 44.12. That matches the value we calculated in the other two methods. Okay, so there's our 0. There's our 44.12. And if I take the dimension from 0 to 0.2, I'll get the 15.58. Again, it's a driven constraint. So here are my two normal stresses. The other thing I can do is figure out what the maximum shear stress is. The first thing I'll do to do that is I'm going to put a point up here on this top quadrant right there. And again, it's green, so I'll hit escape to get out of the command, and I'm going to set up a vertical constraint. I want this point to be exactly vertical from the center of the circle. That forces it to be on the top of that quadrant. Then dimension from the center to the top, and the maximum or the maximum principal shear stress is 22.1. So now we have 3 different methods for calculating the principal stress states of a 2D stress cube.